1889, Pittsburgh, Pennsylvania. The structural crisis threatening American construction was hiding behind every bridge collapse and building failure. European steelmakers produced metal through patient artisanal methods requiring weeks of careful temperature control and hand-selected ore processing. American mills struggled with consistency that varied wildly from batch to batch. A steel beam from one foundry couldn't be trusted alongside beams from another. British engineering journals called American steel brittle gambles wrapped in industrial propaganda. German metallurgists shook their heads at American dreams of rapid production. The French masters of crucible steel dismissed American manufacturing methods entirely. Then one man walked into Pittsburgh's steel district with an impossible promise. Andrew Carnegie, a railroad executive turned industrialist, claimed he could produce structural steel faster, stronger, and more consistent than anything Europe had ever achieved. That's a quality sufficient to support buildings reaching heights previously thought impossible. European experts laughed. Metallurgical science itself seemed to prove him wrong. Rapid production created internal stresses, speed prevented proper carbon distribution, and volume manufacturing made quality control impossible. But deep in the Monongahela Valley's industrial heartland, something extraordinary was taking shape. The process that would make European steel masters question everything they thought they knew about metallurgy. The morning smoke hung over Pittsburgh's mill district as Andrew Carnegie stepped through the gates of his expanding steelworks. The November chill of 1889, carrying with it the familiar sounds of American ambition grinding against European contempt. Steam roared from blast furnaces that ran along the riverbank, while the thunderous pouring of molten iron echoed from neighboring foundries where manufacturers struggled with the same crushing reality that drove Carnegie's obsession. American construction was being strangled by unreliable materials. Carnegie paused outside his office, watching workers transport steel ingots between cooling beds. Each piece supposedly produced to standard specifications, yet requiring individual testing before any structural application. The irony burned hotter than his furnaces each morning. His company, Carnegie Steel, had built a reputation for ambitious production targets and aggressive pricing. Yet they couldn't solve the fundamental problem choking American development. There was no consistent American steel. Every mill, every batch, every production run operated with different material properties and unpredictable structural characteristics. A steel girder cast in Pittsburgh measured differently in tensile strength from a beam produced in Bethlehem. The variations ranged by thousands of pounds per square inch, making reliable structural engineering impossible. The consequences rippled through every corner of American development. Bridge builders couldn't guarantee that components from different suppliers would bear calculated loads. Railroad companies faced nightmares when steel rails from multiple sources fractured under identical operating conditions. The emerging skyscraper industry struggled to achieve the material reliability that would make tall building construction economically viable and structurally safe. Each finished structure required engineers to over-design with excessive material, defeating the entire economic advantage of steel construction over masonry. European competitors observed American struggles with barely concealed satisfaction. British metallurgical journals published devastating assessments of American steel production, describing it as quantity masquerading as quality, speed replacing craftsmanship. German steel masters who had spent generations perfecting crucible methods shook their heads at American attempts to rush processes requiring patient temperature control and careful chemical monitoring. The French inventors of advanced steel alloys dismissed American production methods as fundamentally incompatible with metallurgical quality. The technical objections seemed insurmountable. Traditional steelmaking required slow cooling cycles that allowed internal stresses to dissipate naturally, demanded careful temperature ramping that distributed carbon content evenly, and depended on small batch production where master steelmakers could monitor quality through visual observation and tactile testing. Even the basic definition of quality steel varied from region to region, as European traditions had evolved independently without scientific standardization. Master steelmakers in Sheffield and Essen had developed production techniques over centuries of guild apprenticeship, achieving material properties through experience and intuition that mechanical testing couldn't replicate. European armorers and toolmakers in particular took pleasure in American metallurgical failures. They had perfected slow production techniques that created steel of exceptional consistency, with each batch carefully monitored throughout multi-week production cycles. Why rush toward volume production when traditional methods guaranteed superior results? Their foundries operated like medieval workshops, with knowledge passed down through generations of craftsmen who understood steel quality as an art form rather than an industrial commodity. The numbers told a devastating story. European master steelmakers could achieve tensile strengths of perhaps 60,000 pounds per square inch on their finest batches using techniques refined through decades of careful experimentation. American steel, by contrast, varied from 40,000 to 70,000 psi, even within individual production runs. The inconsistency wasn't merely technical but philosophical. Europeans viewed steel quality as the culmination of patient craftsmanship and generational knowledge. Americans sought systematic methods that could be measured, controlled, and replicated at industrial scale. Carnegie understood the stakes extending far beyond his company's profitability. American architectural independence hung in the balance. The nation that had achieved political sovereignty remained structurally dependent on European material superiority. If American steelmakers couldn't achieve consistent quality, they would forever occupy secondary positions in global construction markets, building structures designed and approved by European engineering standards. The financial pressures intensified daily. Construction contracts demanded reliable steel specifications, but domestic suppliers couldn't deliver without abandoning the production volumes that made American pricing competitive. Architectural firms, having witnessed multiple structural failures of American steel construction, grew increasingly skeptical of domestic materials. Major building projects in New York and Chicago maintained relationships with British steel suppliers precisely because American companies couldn't guarantee the consistency that tall building construction required. Carnegie's partner, Henry Clay Frick, shared the frustration driving their search for solutions. Both men had invested everything in American industrial-scale production, betting their fortunes on systematic manufacturing surpassing European craft traditions, but ambition alone couldn't overcome the metallurgical crisis paralyzing the construction industry. The breakthrough would require approaching steel production with entirely different assumptions. Instead of fighting the variables inherent in rapid production, Carnegie needed measurement and control systems that could monitor those variables systematically. Instead of slowing production to match European craft methods, he needed scientific understanding of what actually made steel strong and consistent. The solution demanded collaboration between metallurgical science and industrial engineering. Academic understanding of iron-carbon chemistry needed to merge with practical manufacturing knowledge of large-scale production realities. The challenge wasn't simply building bigger furnaces, but creating entirely new approaches to quality control that could achieve consistency through systematic monitoring rather than artisanal intuition. Carnegie assembled an unprecedented team of technical specialists in early 1890. He recruited Alexander Lyman Hawley, America's foremost Bessemer process engineer, who brought systematic understanding of how rapid steel conversion affected material properties. Julian Kennedy joined railroad engineering, contributing practical knowledge of the structural requirements that made steel trustworthy for load-bearing applications. Charles Schwab arrived from Carnegie's Homestead Works, understanding industrial production realities where theoretical quality needed to meet daily tonnage targets. Together, they represented the merger of scientific metallurgy with industrial-scale manufacturing that had never been systematically attempted in American steel production. Their conversations revealed the magnitude of innovation required to achieve consistent quality at unprecedented production volumes. Hawley explained how Bessemer conversion created material consistency by burning impurities from molten iron in controlled atmospheric conditions, producing steel with predictable carbon content if temperature and timing were precisely managed. Kennedy recognized immediately that similar systematic control could address the structural reliability problems plaguing American construction if they could design monitoring systems accurate enough to verify material properties during production rather than through post-production testing. The breakthrough concept emerged during their first month of collaboration. Instead of accepting batch-to-batch variations as inevitable consequences of large-scale production, they would design inline quality monitoring that caught problems during manufacturing when corrections were still possible. Hawley had observed how railroad maintenance shops tested steel rails after installation failures, conducting destructive tests that revealed internal flaws invisible during production. Kennedy realized that applying systematic testing during manufacturing could prevent structural failures by catching defective material before it reached construction sites. Their design approach borrowed directly from scientific laboratory methodology. Metallurgical research required testing material samples under controlled conditions to understand how production variables affected final properties, using systematic measurement that transformed steel quality from subjective craftsman judgment into objective scientific data. Carnegie proposed testing protocols requiring regular sampling from every production batch, where material specimens would undergo tensile testing, chemical analysis, and microscopic examination before any steel left the mill. Schwab recognized that such comprehensive testing required laboratory facilities and trained technicians far exceeding current American steel industry capabilities. The Chemical Analysis Laboratory became their central innovation. Hawley had worked with European metallurgists who used spectrographic analysis to determine precise carbon and silicon content in steel samples, employing scientific instruments that could measure chemical composition to fractions of a percent. Carnegie adapted this laboratory technique for production line application, designing facilities where trained chemists could analyze samples and adjust furnace operations in real time based on systematic chemical testing. By summer 1891, Carnegie Steel's Edgar Thomson Works had implemented the most sophisticated quality control system ever attempted in American industry. Chemical laboratories operated around the clock, analyzing samples from every heat of steel produced. Mechanical testing facilities subjected sample bars to tensile and compression loads that revealed material properties with scientific precision. Metallurgical microscopes examined grain structures that indicated proper heat treatment and carbon distribution. The systematic approach transformed steel production from craft tradition into measured science. The breakthrough results arrived faster than Carnegie's team had anticipated. Steel from the Edgar Thomson Works showed consistency that exceeded European craft production, with tensile strengths varying by less than 2,000 psi across entire production runs. Chemical analysis revealed carbon content controlled to within 0.05%, achieving uniformity that hand-selected European methods couldn't reliably match. The systematic quality control had accomplished what Carnegie promised: industrial-scale production delivering material reliability, surpassing artisanal techniques. Construction engineers began noticing the difference immediately. George Post, designing New York's first steel frame skyscrapers, found that Carnegie Steel allowed structural calculations with confidence previously impossible using American materials. The beams arrived with certified test results showing exact material properties, eliminating the safety factors that made American steel construction economically prohibitive. Bridge engineers discovered similar advantages as Carnegie material enabled precise load calculations that reduced steel requirements while increasing structural safety margins. The Chicago architectural firm of Burnham and Root, planning the Masonic Temple building that would become the world's tallest structure, specified Carnegie steel exclusively after testing revealed consistency that made their ambitious height calculations viable. William LeBaron Jenney, pioneering steel frame construction for the home insurance building, found Carnegie material reliable enough to trust his revolutionary structural system, where the steel skeleton carried all building loads. European engineering delegations began arriving in Pittsburgh by late 1891, expecting to find typical American overstatement masquerading as technical achievement. Instead, they encountered systematic quality control that challenged fundamental assumptions about steel production methodology. British metallurgists from Sheffield examined Carnegie's chemical laboratories with growing recognition that American systematic testing surpassed British craft judgment for ensuring material consistency. German steelmasters studied the mechanical testing protocols and acknowledged that objective measurement provided reliability that subjective craftsman experience couldn't guarantee across large Production volumes. The international visitors returned home with reports describing American innovations that traditional European methods couldn't match through individual skill alone. Carnegie's confidence grew with each successful application of his systematically produced steel. Railroad companies began specifying Carnegie rails exclusively after finding that systematic quality control eliminated the catastrophic failures plaguing American track systems. The Pennsylvania Railroad, America's largest carrier, contracted for Carnegie steel after testing revealed material consistency that made their expanding network structurally reliable. Bridge contracts followed as engineering firms recognized that systematic testing made Carnegie steel trustworthy for critical load-bearing applications. By year's end, Carnegie steel had established American systematic production as competitive with European craft methods, achieving quality through measurement and control rather than generational artisan knowledge. Yet success brought scrutiny that would test whether systematic quality control could survive the brutal pressures of industrial-scale manufacturing. The disaster struck on a humid July morning in 1992 when labor unrest at Carnegie's Homestead Works exploded into violence that would test whether systematic quality control could survive social chaos. The Amalgamated Association of Iron and Steel Workers, facing wage cuts and threatened displacement by Carnegie's mechanized production methods, launched a strike that paralyzed operations at the company's largest and most sophisticated mill. Henry Clay Frick, managing Carnegie's operations while the owner vacationed in Scotland, responded with private security forces whose confrontation with strikers turned the Homestead Works into a battlefield. Production collapsed completely as violence drove skilled workers from the facility and destroyed the careful operational discipline that systematic quality control required. The steel quality crisis emerged gradually as Carnegie struggled to restart production using replacement workers lacking the training and experience that systematic testing demanded. Chemical laboratories sat idle without trained analysts to interpret results. Mechanical testing equipment remained unused as inexperienced operators couldn't distinguish normal variations from dangerous defects. The systematic quality control that had achieved unprecedented consistency depended on skilled personnel whose absence destroyed the entire methodology. Within weeks, Carnegie steel quality began deteriorating toward pre-1890 inconsistency. Construction projects using material from strike-affected production runs reported structural problems that hadn't occurred with pre-strike Carnegie steel. A railroad bridge in Ohio developed dangerous deflection under load. Investigation revealed that steel beams supplied during the strike period showed tensile strengths 15,000 psi below specifications. A Chicago building project discovered column failures during construction, testing indicating that replacement worker production had created material with unpredictable properties. European competitors seized on the Homestead crisis with barely concealed satisfaction. British steel journals published accounts describing how American systematic methods had collapsed under social pressure, proving that industrial-scale quality control remained fundamentally vulnerable compared to stable European craft traditions. German steelmakers cited the quality failures as evidence that mechanical testing couldn't replace human craftsmanship developed through generations of guild apprenticeship. The crisis threatened everything Carnegie had built. Construction firms that had embraced Carnegie steel began reverting to European suppliers whose craft methods seemed more reliable than American systematic production vulnerable to labor disruptions. Architectural practices canceled pending Carnegie contracts, unwilling to risk structural failures from material whose quality could no longer be guaranteed. Railroad companies initiated reviews of Carnegie rail specifications, questioning whether systematic quality control could maintain consistency under real industrial conditions. Carnegie rushed back from Scotland in August to confront a crisis that threatened his company's survival and vindicated every European criticism of American steel production methods. The Homestead Works, which had represented the pinnacle of systematic quality control just months earlier, now symbolized the fragility of industrial methods compared to traditional European craft stability. His systematic approach to steel quality had proven vulnerable to the social disruptions inherent in American industrial labor relations. The quality collapse revealed that systematic testing alone couldn't ensure consistent production. The methodology required a stable, trained workforce that American industrial conditions couldn't guarantee. European steelmasters who had acknowledged American innovation now dismissed the systematic approach as fundamentally flawed for practical manufacturing under real-world pressures. Carnegie refused to abandon systematic quality control despite overwhelming evidence that labor instability had destroyed confidence in American steel production methods. He spent the fall of 1892 completely reimagining how systematic testing could function independently of workforce stability, studying production methodologies that could maintain quality control even during operational disruptions. His engineering intuition suggested that automation and procedural standardization could create consistency that didn't depend entirely on skilled human judgment. The revelation came to Carnegie during late-night discussions with Julian Kennedy at the Edgar Thomson Works. Kennedy had been documenting exactly where quality control had failed during the Homestead crisis, identifying specific points where human judgment and manual operations had introduced the variability that systematic testing was designed to eliminate. Carnegie realized suddenly that their original approach had automated testing but not production control. Chemical analysis revealed problems, but fixing those problems still depended on manual furnace adjustments requiring skilled operator judgment. The breakthrough understanding emerged from recognizing that systematic quality required automating not just measurement but the production variables that measurement monitored. If chemical testing showed excessive carbon content, automated systems needed to adjust furnace conditions without human interpretation. If mechanical testing revealed insufficient tensile strength, standardized procedures needed to correct heat treatment automatically rather than through craftsman intuition. Carnegie's solution required complete reconceptualization of how systematic production achieved quality. Instead of merely testing finished steel and accepting or rejecting results, he needed closed-loop control systems where testing automatically adjusted production variables to maintain specifications. This meant designing furnace controls that responded directly to chemical analysis, heat treatment systems that automatically modified based on mechanical testing, and production protocols that removed human judgment from quality-critical decisions. The engineering challenges demanded innovations pushing American steel industry capabilities beyond existing limits. Carnegie designed automated temperature controls that maintained furnace conditions within precise ranges using thermocouples and mechanical feedback systems. Chemical analysis protocols were standardized into procedural checklists that minimized operator interpretation, while mechanical testing became automated to the extent that specimen preparation and load application followed fixed sequences requiring minimal skilled judgment. Charles Schwab returned to Homestead in early 1893 with renewed determination to implement the lessons learned from the strike crisis. The mill had resumed operations with a replacement workforce, but now featured automation and procedural standardization that made quality control less dependent on individual worker skill. Chemical laboratories received instrumentation that automated sample analysis, reducing interpretation requirements. Mechanical testing adopted standardized specimen geometries that eliminated variation from sample preparation. Furnace operations implemented feedback controls that adjusted automatically based on testing results. The reconstructed production system incorporated hard-learned lessons from the strike disaster with engineering sophistication exceeding the original 1891 design. Automated controls maintained temperature stability that manual operation couldn't achieve consistently, while standardized procedures eliminated the judgment variations that workforce turnover had introduced. Quality control protocols were redesigned to function reliably even with less experienced BA personnel, proving that systematic methods could achieve consistency through automation rather than depending entirely on skilled labor. By mid-1893, Carnegie steel quality had recovered to pre-strike consistency despite continued workforce tensions at Homestead. The automated quality control systems maintained material specifications that exceeded original 1891 performance, while production volumes reached levels that craft-based European methods couldn't economically match. Carnegie's systematic approach had survived its greatest test, proving that industrial-scale quality could be sustained through engineering rather than traditional craft methods. The Masonic Temple building opened in Chicago in Tang, its 302-foot height supported entirely by Carnegie steel that had performed exactly as structural calculations predicted. Engineers marveled that American systematic production had delivered material reliability, making the world's tallest building possible. The structure stood as physical proof that Carnegie's methods surpassed European craft traditions for critical structural applications. Railroad bridge projects across America adopted Carnegie steel exclusively after the company's quality recovery demonstrated that systematic control could maintain consistency even through operational crises. The Pennsylvania Railroad expanded its Carnegie contracts, recognizing that automated quality systems provided reliability that European craft methods couldn't guarantee across the enormous steel volumes that American railroad expansion required.